So, welcome to lecture 5 of the course Solar Photovoltaics Principles, Technologies and Materials. So, in the last lecture we looked at, we will just do the brief recap. So, in the last lecture we looked at effect of let us say longitude or location on local solar time. So, essentially we looked at a few expressions, and since you can understand this very well because for example for this country we calculate the time which is 5:30 hours ahead of GMT, okay. But India is a vast country and the longitude varies by at least 5 to 10 degrees. As a result, time in different locations cannot be same, hence the solar noon will not be the same. So, for example, if you go to far east of the country, the sun rises earlier, whereas if you go to the western part, the sun rises later, whereas the clocks are set at the same time. So, as a result, there is a difference between the time when the sun is at zenith, that is actual noon, with respect to the noon that is shown by your watch. So, correct for these differences, we looked at certain expressions by which you can calculate the time correction which will correct the solar time, that is, which will help you to calculate the time at which the actual time at which the sun will be at the zenith. So, that is useful from the perspective of calculation of solar radiation intensity, whose details we will see later on. So, now we will look at some more details of geometrical relationship between earth and sun. So, we will first look at a quantity called as hour angle, which is called as omega, and this is depicted as HRA, okay. So, HRA is essentially angular measure of time, okay, and it converts, so basically it converts LST into number of degrees by which the sun moves through the sky, okay. So, basically it converts the time into number of degrees. So, HRA is depicted as 15 degrees into LST minus 12. So, by definition hour angle is 0 at solar noon. So, of course, when you have solar noon, then LST is equal to 12, and which means this is 0 degree at solar noon. So, you can see that in the morning this is negative, it is negative in morning and positive in afternoon. If you look at the rotation of earth around the sun, so this is our sun, okay, and around which you have the orbit in which the earth moves, and this is our earth, okay. And for earth there is something called as an axis. This is axis of earth, axis of rotation of earth around which it is rotating. So, this is sun, this is earth. So, there is certain thing called as declination angle, because this axis is not parallel to the orbital axis. As a result, you have weather changes, okay, and this is depicted in the form of what we call as declination angle. So, this gives rise to an angle called as declination angle, and so earth goes through various locations. So, around this point you have let us say this is June and this is December. So around December 23 you have winter solstice. Okay. In June you have summer solstice. What it means is that the declination angle is minimum, that is it goes through a value of minus 23.49 degrees in winter. In summer it goes through plus 23.49. So we are taking this for northern hemisphere, and then you have March 22 you have equinox, when this angle delta is equal to 0. So this angle is called as delta. And then you have September 23 when you have equinox, then again delta is equal to 0. What it means is that because of this axis of Earth's rotation being tilted, you have shortest day, that is in December, which would mean for shortest day for northern hemisphere, whereas it would be longest day for southern hemisphere. You have March 22 which is equinox, which means day and night are equal, and that is when this lambda is equal to 0. I will explain to you what lambda is in a minute. And then we have June's summer solstice when the day is the longest, and then we have September 23 when the day and night are again equal in length. So because of this eccentricity, it goes through these seasonal variations, and the way we calculate this angle as, so you have this Earth, let us say, now we draw it with respect to Earth. So this is Earth, okay, this is the vertical axis, this is the, let us say your sunlight is coming from this direction, so this is sun ray, and this is, let us say, the north, and this would be south, north-south axis, and this is where we have equator. So this is equator. So here this angle, whatever we see here, with respect to this vertical, this angle is called as the declination angle, or you can say, since this angle is delta, the angle between the horizontal and the equator, the horizontal is parallel to the sunbeam. So angle which is made by sun ray with respect to the equator, that is again is called as delta. So this is the declination angle delta, and this changes because this north-south undergoes a rotation, because this does not remain in the same position all the time. This delta also changes as a function of time. So this delta varies as function of time of the year, because Earth tilt is also changing throughout the year. So let us say in the, if you again plot Earth, so in the summer solstice, this is the sun, so this is the declination, which is 23.49 degree. I will give you the formula in a little while, or maybe I can write the formula just now. So the way you calculate the way this declination angle is worked out, this declination angle is defined as delta is equal to 23.45 degrees into, sorry, it's 45 not 49, sine of 360 divided by 365 into n minus 81, or you can also write it as n plus 284, because if you sum them up, it is nothing but 365. Okay. So this is the expression. So you can substitute n minus 81 by n plus 284 and to get the same value. So declination angle is basically an angle which is made by joining the center of the sun and the earth with its projection on the equatorial plane. Okay. So, when you look at June 23 in summer solstice, the sun, so this is the angle between the sunbeam and the equatorial plane. Okay. So, this is 23.45, the maximum it can achieve. If you look at now other position, so other position would be, right. So, this is when the angle is, so if this is sun, then the angle is equal to 0 degree. When would that be? Spring equinox, right. And if you take it to the other side, it will be the other equinox, March equinox.
June 21 or June
23.
23?
What was it? Let me just see. It is June 23. June 23. Just one second. Let me check. June 21. You are right. Yeah, it's June 21. It is June 21 here. And again it is June 21 here. Okay. And sorry, December is 23. And then we go for the winter one. So, this is Earth, Sun, and for the winter one you would have Sun somewhere here, and this would be the angle which is minus 23.45 degree. Okay. So, this would be December 23. All right. So, this is winter solstice, this is summer solstice, this is equinox, and let me just correct the values. This is 4.5. Okay. So, the first angle that we have worked out is delta, which is the declination angle, is 23.45 degrees multiplied by sine of 360 divided by 365 into n minus 81. So, naturally you can see the value changes from plus minus 23.545 to plus 23.45 degrees as a function of day of the year. So, if you plot the values, so let us say when we plot the values from December 23 to December 23, let us say, so this goes from so somewhere here we will have June 21. So, this will go from minus 23.45 to plus 23.45 back to minus 23.45. So, this would be plus 23.45 degrees. This is how it will vary throughout the year, and somewhere in between it will go through 0 degrees. So, you will have 2 times. So, this would be your, these will be your equinoxes when delta will be equal to 0 degrees. Okay. So, equinox 1 and this will be equinox 2 in March and September. And then we define some more angles. We will go a little quickly. So, the first angle that we define is called as elevation angle or altitude angle, which is called as alpha. This angle is defined as the angle between sun ray and its projection on horizontal plane. So, let us say this is the vertical, this is the horizontal plane, this is sun, this is the sun beam that is coming. So this is the value which is called as elevation. So you can say this is alpha, okay, right. And when you calculate, so this is, let us say, horizontal plane, this is sun. Next angle that we determine is zenith angle. Zenith angle is the angle between sun ray and a normal. So essentially this is the normal, this is the horizontal, this is the sun, and this is a sunbeam. The angle here is called as theta z. This is normal. Under certain conditions, theta z plus alpha will become equal to 90 degrees, but they will not be 90 degrees for all the conditions, because remember the sun always moves from north to south in the sky, okay. So those two angles will always not match equal to 90 degrees, the sum, but under certain conditions they will become equal to 90 degrees. And then we have third angle called as solar azimuthal angle. The angle which is in the horizontal plane between north south line and projection of sun ray on the horizontal plane. So let me just draw it for you. So if this is the horizontal plane, all right, and if I define this north, this is south, east, this is west, let us say sun is somewhere here. Okay, so this is sun, and so this is the sun ray, right? This is the projection. So this is projection, this is the north south line, this is the angle which is gamma, yes, the solar azimuthal angle. So you can see naturally the solar azimuthal angle will, so if you are going from east to west, so if it is in east, it goes to plus 90 degrees, and if you go to west, it goes to minus 90 degrees. So basically then we can, so using these angles we can frame a general framework, we can make a general framework. So general framework of geometrical relationship for an object that is kept at an angle with respect to the horizontal. So most of the things that we have seen so far are for the horizontal surface, but the solar panel on the surface is kept itself on a certain angle. So you need to also bring that angle into account. So this is, so generally what will happen is that this is your horizontal, and somewhere here you will have inclined surface. So this is your surface which receives the radiation, and this is your horizontal. So that itself makes an angle called as beta, okay. So this is what we need to C. So let me show you a PPT. Look at those relationship. So this is basically a figure which shows you the relationship of a surface, let's say a solar panel, which is inclined with respect to horizontal at an angle beta. So essentially we are going to look at the relationship between various angles for an inclined surface. So sun surface geometry for an inclined surface. So this gray one is the surface which is inclined at an angle beta with respect to horizontal, and the south is pointing in the direction which is shown by this arrow. Now detailed analysis of this whole thing you can see in this reference which I have noted here. So it's Brown and Mitchell, Solar Energy. It's a paper which got published in 1983, and this has a detailed geometrical analysis of these relations. So unfortunately we don't have enough time to go through these, but we'll just look at various segments of it, key segments. So this is the vertical with respect to the horizontal surface, okay, and this is the sun, okay. So sun beam is the red one which is coming for a given point. So this angle which is between the sun ray and the vertical is theta z, alright, and this is the normal to the surface, okay. Normal to the surface doesn't necessarily mean the sun beam. You can have a normal to the surface at a different angle. So this angle which is the normal to the surface and the sun is the theta angle theta, and this some angle theta, okay, and this is what we are interested in calculating, the angle between the sun beam and the normal to the surface. So I can first calculate what is the solar azimuthal angle. Solar azimuthal angle is the angle between projection of sun beam on the horizontal and the north south direction, which is gamma s. And there is another azimuthal angle which is the projection of north of the surface on the north south plane. So this is normal to the surface. If I take its projection on the north south plane and then calculate its angle with respect to the north south axis in the horizontal plane, then this angle is gamma. And then there is a angle which is the angle between the vertical to the horizontal and the normal to the surface. This angle is gamma s minus gamma, that can be shown by geometry. So if I say that this point is A, this point is B, this point is C, then this makes a spherical triangle, and we know various angles between these. If I know these angles and I consider this ABC as a spherical triangle, then if I apply the law of cosines to this spherical triangle, then first thing that I work out is cos theta is equal to cos theta z into cos beta plus sin theta z sin beta into cos gamma s minus gamma. There is the first relation that I get for cos theta. Alright, and then I have this another figure in which I can now correlate these angles in a little different form. So what I have done is here I have now taken it with respect to earth. So O is the center of the earth, this is the direction which is to the sun. So this is basically the beam. This is the vertical which is with respect to the horizontal surface, okay, and this is the vertical which is with respect to horizontal surface. Horizontal surface doesn't necessarily need to be, see, horizontal doesn't mean equator. The equator and the horizontal are two different things. For certain location horizontal will be equal to equator, but for certain other location, for example if I am sitting in China, the horizontal is not the equator. But if you have a country which is located on the equator, then horizontal is equal to equator. So horizontal and equator doesn't necessarily mean the same thing, it is location dependent. So as a result, the vertical is not necessarily the north axis. As we saw in this figure earlier, this is south, north is in that direction, and north and the vertical do not necessarily coincide. That is dependent upon the location. So similar, that is what I am trying to show in this location. So if you represent the same figure with respect to the earth, then we have this, so this is north of the earth, on this side you will have south, this is the vertical with respect to horizontal, this is the sun ray, and then again you can make a triangle which is NP and Q. So this angle between NP and NQ is the hour angle, HRA, and the angle between P and Q is the zenith angle, because sun ray and the vertical are they constitute theta z. And similarly, if you look at this P location, P is the location which is essentially the location at which you are with respect to equator. So this is nothing but your latitude. Okay, so this is latitude. So this latitude is the angle between equator and the point P. Gamma S is the solar azimuthal angle, which is the angle between. So if you look at gamma S is the angle between the sunbeam, its projection on the horizontal plane, with respect to the north south. So gamma S is this is north south, and this is sort of, you can say, one great circle. This is, you can say, another great circle. So essentially the angle between these two. So this green line is the one which you can say, so this is P and Q. P is the location which depicts the vertical, and Q is the direction of the sun. So if you again go back to previous figure, just try to correlate this. Gamma S is the angle between sunbeam projection, this is that projection, with respect to north south. So this is the vertical axis north south of Earth's axis, and or you can say horizontal, not Earth's axis, but with respect to the horizontal. So this is north south, and then you have this projection, and the angle between these two is gamma S. So this is the angle which is represented as this angle between these 2 points, the green line PQ and this latitude. So this basically is with respect to Earth's position, and this is the position which is, you can say, the sunbeam and its projection on the north south plane. So the angle between those two is gamma S. So if you apply again so we can see that P is the point of observation at hour angle omega, Q is the sun normal point, and O is the center of the earth. So for NPQ, again when you apply law of cosines, you get a relation for cos theta z, and this cos theta z turns out to be sin delta sin phi plus cos delta cos phi cos omega. And again when you apply law of sines for NPQ, you get sin gamma S is equal to sin omega cos delta divided by sin theta. So I don't have time to get into the proofs of these, but if you want to get into the details of the proof, you can refer to this paper which I referred earlier. So these three equations, when they are combined for various conditions, they give you certain geometrical relationships. So for example, to simplify the matters, if you have a vertical surface which means beta is equal to 90 degree, then cos theta can be simplified by combining the above three equations as sin phi cos delta cos gamma cos omega minus cos phi sin delta cos gamma sin beta plus cos delta sin gamma sin omega. This is the first relation that gets modified for a vertical surface. Similarly, for a horizontal surface, this, which means beta is equal to 0, then again this equation gets modified, and this becomes very simple equation in that case. Cos theta is equal to sin phi sin delta. For a horizontal surface, theta is theta z. So theta gets modified to, so this theta is nothing but theta z in that case, cos phi, cos delta and cos omega. So likewise you can do various things. For example, you can have a surface facing south. If surface itself is facing south, which means gamma is equal to 0, because then the projection of vertical coincides with the north south, as a result gamma is equal to 0. So cos theta then again gets modified to sin delta into sin phi minus beta plus cos delta cos omega into cos phi minus beta. And if you have a vertical faces which is due south, then again it gets modified to simpler equation. So those equations are complex, but they can, so by looking at these simple variations or simplistic expressions, you can modify those expressions to much simpler forms. So we'll cut here. I think we have run out of time. The remaining exercise of this geometrical relationship we can do in the next class. Thank you.